It's my pleasure to open our seminar. I am Amir Gogatishvili and I will be today chairman of this talk. Our speaker today is Wentao Teng from Kwansei Gakuin University. I'm sorry for transcriptions. And he will be speak about translation, Dunkl-type BMO space, and Riesz transform for Dunkl transforms on L infinity. Please.
Thanks for your introduction. The topic of my talk is Dunkl translations, Dunkl-type BMO space, and the Riesz transform for Dunkl transform on L infinite. The talk is based on the paper published on functional analysis and its applications. We studied some generalization of some results in classical Fourier analysis to the content of Dunkl theory. Because of some differences of Dunkl translations and the classical translations, such generalization involving the Dunkl translation will usually be non-trivial. We review the definition of the classical BMO space first. The BMO space is defined by the space of all those functions in L1 local, defining this norm is finite, where the norm is defined by the supreme of this mean oscillation. We consider the function defined by a constant be the same element in BMO space to let this be a norm. The ordinary Riesz transform is defined as this. It is the principal value of this integral. It is well known that the Riesz transform is bounded on L2 and the kernel satisfies the heterodyne condition. And so the Riesz transform is bounded on LP. And from completely supported functions on L infinite to BMO space. But to prove the boundedness from the whole space of L infinite to BMO space, we need to extend the definition of Riesz transform to L infinite first. Because the completely supported functions are not things in L infinite. Here are many methods on the extension of the definition of Riesz transform to L infinite. Here is only one of the methods by figure -10. They minus the original Riesz transform by a constant. Then this extension can be seen as the same element in BMO space as the original Riesz transform. And this integral is convergent for fixed x and y from heterodyne condition. We studied some related problems about Riesz transform in Dunkl theory. Dunkl theory is a function generalization of classical Fourier analysis related to row system. We will extend analogous results in classical Fourier analysis to the context of Dunkl theory. In the past 20 years, there have been many related results. In 2020, Amr and Sifi proved the LP boundedness of Riesz transform for Dunkl transforms. In 2019, Anker, Dubansky, and Hajna characterized the real study space with Riesz transform in Dunkl setting. This is my result. It is about the boundedness of Riesz transforms for Dunkl transform from L infinite to Dunkl-type BMO space and function. It is one step towards the duality of hard space and BMO space in Dunkl setting, which is an open problem of great interest. We then introduce some notation and definitions in Dunkl theory. The reflection sigma with respect to this hyperplane is defined as this. The root system is a finite set in Rn, they find that it is invariant under the reflection for NF in the row system. Here are two examples on the row system in R2. The reflection group of the row system is the finite subgroup G of O(n), the orthogonal group generated by the reflections. The multiplicity function is a G-invariant function from the row system to the complex domain. We assume that K is no less than 0. The homogeneous dimension of the row system is the dimension plus the sum of the multiplicity function. The Dunkl-type measure is defined as this. It is invariant under the finite reflection group G. The measure is in substitute of the big measure in classical analysis, which is invariant under the orthogonal group. So we say that the reflection group G plays the role of the orthogonal group in classical analysis. The Dunkl-type measure of this ball is equivalent to this. So the measure is a doubling measure. Here Pxr is a closed ball. The Dunkl operator is defined as this. It is the deformation of the partial derivative by the different operator. They are analogous to the partial derivative in classical analysis. They commute pairwise and are square symmetric with respect to the Dunkl measure. Dunkl Laplacian is defined as this. The minus Laplacian is essentially self-adjoint and positive definite, and so the Laplacian is the generator of the compressed stem group. The Dunkl kernel is a unique analytic solution to the differential equation system. The Dunkl transform is defined as this via the Dunkl kernel. Here, the Dunkl kernel takes the place of the exponential function in classical Fourier transform. Obviously, the Dunkl transform of the Laplacian of f is this, and we have these equations. It is analogous to the classical Fourier transform. The Dunkl translation operator is defined on L1 via the Dunkl translation, or via the Dunkl transform. It has analogous properties to the classical translation. From the square symmetry, the Dunkl translation can be defined on LP in distributional sense. Further, for Schwarz functions, the integral of the Dunkl translation of f is equal to the integral f. But for all functions on L1, this equation holds only for radial functions on L1. But we are not sure whether it holds for all functions on L1 because the Dunkl translation, because it is still unknown whether the Dunkl translation is a boundary operator on L1. For radial functions, the Dunkl translation can be represented as this. Here, μx is the probability measure with the support contained in the common hole of the orbit of x, and the orbit of x is contained in the support of μx if k is more than 0. Here, k is more than 0 means that every index of k is more than 0. The formula was proved by Riesz for Schwarz functions and was then extended to all continuous radial functions by then 1. This shows that Dunkl translation is partial on radial functions because μx is a probability measure. From the symmetry of Dunkl translation, along with a result by Gallardo and Riesz in 2016 for Schwarz radial functions, we can get this equation for radial Schwarz functions. The distance of orbits of Jx and Jy is defined as this. It has additive and symmetry property. It's easy to say that AXY it is less than the maximal value when it takes Jx, and no less than the distance of orbits. Let B star be the ball with double radius and Q star be the union with the orbital ball. Then they belong to the complementary set of Q star, and equivalent to that, the distance of orbit is more than 2r. Dunkl collusion is defined as this via the Dunkl translation, or can be written as this via the Dunkl transform. It has analogous properties to the classical collusion. We then study some properties of the support of the Dunkl translation. If F is in L2 and the support F is contained in this ball, then the support of the classical translation of F is contained in this ball. But what about the support of the Dunkl translation of F? Some of the she studied via Palamin approach. They found that the support of the Dunkl translation of F is contained in this large ball. Here, the distance from X to this boundary is R. Amory anchored the surface and studied further. They found the support could be much smaller. It is contained in this hollow ball. Here, the distance from X to this boundary is also R. Dunkl and then got a much precise result. They found that the support is contained in the union of these balls. It is a precise result if the multiplicity function k is more than 0. Because if k is more than 0 and f is this characteristic function, then the support of the Dunkl translation of f is precisely the union with these balls. We will extend such preciseness to all non-negative radial function L2. This is my result. If the multiplicity function k is more than 0, and let f be a non-negative radial function on L2 with this support, then the support of the Dunkl translation of f is precisely the union of these balls. This means that the current preciseness is not only for this characteristic function, but for all non-negative radial functions on L2. It is sufficient to prove that this inclusion. We prove for continuous non-negative radial functions first. Suppose there is this y in the union with these balls, for which y doesn't belong to the support, which means the attendance of an x such that for any z in the neighborhood of y, this is equal to 0. Then we get this function is 0 for any it in the support of the probability measure. because f is continuous and non-negative. From the orbital x is contained in the subgroup of mu x when k is more than 0. For the orbital J, we can select J to be it to be Jx. Then we get that f z minus Jx is 0. For any zy in the neighborhood of y minus Jx, z1 plus Jx is contained in the neighborhood of y. And so fz1 is 0, which means that y minus Jx is not in the subgroup of f. And but the norm of y minus Jx is no more than r. And this leads to a contradiction to that the subgroup f is divisible. We then prove for all non-negative radial functions on L2. It is from the density of continuous functions with complex support in L2, along with the positivity of Dunkl translation of radial functions. From the density, there exists a sequence of continuous non-negative radial functions, Jn, with this support, such that f over 2 can be approximated by Jn with respect to L2 norm. So for any non-negative smooth function phi on Rn with complex support, the integral of Jn phi tends to the integral of f over 2 phi. If the integral of the support of phi intersecting the support of f is not empty, then the integral of f phi is more than 0. So there exists a sufficiently large number of L so that the integral of Jl phi is less than the integral of phi, because this sequence tends to the integral of f over 2 phi, and it is less than the integral of f. If the integral of the support phi intersecting this ball is empty, then for any natural number n, the integral of Jn phi is 0. So the integral of Jl phi is no more than the integral of f phi. They lead to that Jl is no more than f almost everywhere. We act on the Dunkl translation and take the integral on both sides, and the order of inequality will not change, because the Dunkl translation is positive on radial functions. Let D be the complementary set of the support of Dunkl translation f. Then D from the definition of the support, D is the largest open set such that this integral equal to 0 for all phi, satisfying the support of phi is contained in D. So this integral is equal to 0 because it is no more than this integral, and it is non-negative. Therefore, the support of the Dunkl translation of JL intersecting E is empty, and this leads to the result because the Dunkl translation of JL is precisely the union visible from this argument. Some remarks. This theorem doesn't hold for k is no less than 0. For example, take this root atom in R2, then its cosθ group is J22, and the multiplicity function is if the multiplicity function is 0, then the support of the Dunkl translation with the characteristic function is visible. if the multiplicity function is k1 0 and k is more than 0, then the support of the Dunkl translation of the territoriality function is the union of the two balls. Here are some differences between Dunkl translation and the classical translation. Dunkl translation don't form a group. That is, the compilation of two Dunkl translations is no more Dunkl translation. Dunkl translation is not partitive. Here is my example given by someone and Xu. For the case when J is this symmetric group, but Dunkl translation is partitive array functions. For f in L2, and the support of f is contained in the complementary set of this ball, then the support of the classical translation of f is contained in the complementary set of this ball. The Dunkl analog is that if the support of f is contained in the complementary set of this ball, then the support of the Dunkl translation of f is contained in the complementary set of the intersection of these balls. But it cannot lead to that the support is contained in the complementary set of the union of these balls. Due to the differences, the generalization results in classical Fourier analysis to Dunkl setting involving the Dunkl translation will usually be non-trivial. It is well known that Dunkl translation are contractions on L2, but it is still unknown whether it is uniform bounded on LP. Here, this is the uniform boundedness assumption of Dunkl translations. We only need to assume for P is 1 or infinite, owing to this torrent precipitation and score symmetry of Dunkl translations. It has been known that this assumption holds for radial functions and the one-dimensional case, and hence for the D2n case. It is a long open conjecture for all one group J, and there have been many results based on it, and our main result will be based on this assumption. The lead transform for Dunkl transform is defined as this via the Dunkl translation, or can be defined as this via the Dunkl transform. It is analogous to the classical lead transform. Clearly, the lead transform can be written as the composition of the Dunkl operator and the functional power of the minus Laplacian. And the integral converges for f in L2. It is obvious that the Dunkl translation commutes with the lead transforms, and the lead transform are bounded operators on L2. Consider phi n as C infinite function on R, so that it satisfies these conditions. And let phi n be this integral function. Clearly, phi n is the C infinite radial function, and this limit is 1. The nominality convergence theorem is that the limit can be interchanged with the integral. And from calculation, this part is equal to the Dunkl operator acting on this. And this equal to this from the supersymmetry of Dunkl translation, and the commutativity of the Dunkl translation with Dunkl operators. Denoted by Kj if N to be this part, then the Riesz transform can be written as this. And from calculation, this part equal to this. And from dominating convergence theorem, the limit can be interchanged with the integral, and it equal to this. And where Kj is this. And for all functions in L2 with complex support, the Riesz transform of f equal to this for if the orbital x intersecting the support f is empty. It was shown by Amorim the surface that this integral kernel satisfies the Cadoralism condition. The classical Cadoralism condition no longer valid, where it is the distance of 2 points here rather than distance of orbits. It is no longer valid in Dunkl setting. They then proved that the Riesz transform is a bounded operator on LP from the Cadoralism condition. For F in L2 with complex support, if RG star is the other joint operator of the Riesz transform, from the supersymmetry of the Riesz transform, we have the Riesz transform can be written as this. And if the orbital y is setting the support f is empty, the Riesz transform can be equal to this. The Dunkl-type BMO space is defined via the Dunkl translation as this. It is the space of all those functions in invariant locals that find this norm is finite. The norm is the supreme of this mean oscillation. We consider BMO as the question of the Borel space by the space of constant functions to let this be known. This is my result, and we will show that under the uniform boundedness assumption for Dunkl translations, the Riesz transform for Dunkl transform are bounded operators from R infinite to Dunkl-type BMO space. We write the Dunkl translation of f into the two parts. We prove for completely supported function on R infinite first, and then for all functions on R infinite. For completely supported function on R infinite, the Dunkl translation commutes with the Riesz transform, and the Dunkl translation is f is also completely supported. For the second part, J2, we can get this argument. We can get this estimate from the Cadoralism condition in Dunkl setting. Here we use the uniform boundedness assumption of Dunkl translations. For the first part, J1, we use the Holder inequality along with the L2 boundedness of Riesz transform and get this estimate. Here we use again the uniform boundedness assumption for Dunkl translations. Therefore, we can prove the result for completely supported functions. because the Lie transform commute with Dunkl translations on L2. We then prove for all functions on R infinite. We extend the definition of the Lie transform for Dunkl transform to all of R infinite first. The proof will differ a lot with the classical case from here due to the difference between Dunkl translation and the classical translation. It is mainly due to this one. And so we have to decompose, when we have to change the order of the Dunkl translation and the transform first, and then decompose the Dunkl translation wave in such a way. We extend the definition of the Lie transform to all in R infinite. For any function f in R infinite, define the Lie transform as this. We minus the original Lie transform by this constant. We decompose f as the two parts. Then for the first part f1, the Lie transform of f1 converges almost everywhere because f1 belongs to L2. For the second part f2, the Lie transform of f2 is equal to this, because from this argument, for any epsilon and any neutral number n sufficiently large, this kj epsilon n equal to kj. And this integral converges from the Karolym condition. The definitions for the for this transform for Dunkl transforms on R infinite makes sense for any one in BRN. And it coincides with the Lie transform for completely supported function on L2 and Dunkl-type BMO functions, since the two formulas differ by a constant. And the uniform boundedness assumption with Dunkl transition, and by the same argument and for completely supported functions, we can get this estimate. But there remains one step. We need to change the order of the Lie transform and the Dunkl transition. We have this lemma, and the uniform boundedness assumption with Dunkl transitions for any f in R infinite and any fixed s in Rn. The two differ by a constant independent of y for y in BR. This statement is obvious for completely supported functions on R infinite because the Dunkl translation commute with Lie transform on L2, and so they differ by a constant for f in R infinite. So for completely supported function on R infinite, this integral equal to 0 because this is the constant independent y. Then for all functions in R infinite, by partition unity, f can be written as this, and the support of fi is contained in the bounded set di, where di is the constant for open cover over I. Denoted by j as this, then j can be decomposed in this way. Then from this, we take f to be fi, and that this estimate this is table equal to 0. And so it is the content in J is the content independent map on BR. We denote by Cx the content the 2D plus this, then we get this estimate and then prove the result because this part is equal to this and prove the result. That's all my talk. Thank you.